All right, so hi everyone, my name is Kate Sanders. I'm a third year CLSP student here. I'm advised by Ben Van Dermy, and I'm going to be talking about event semantics for visual and multimodal content. So many cognitive scientists argue that visual meaning is multi-layered. So low-level meaning is extracted early in the perceptual pipeline, and then higher-level abstract meaning is extracted later along in the cognition process. But there isn't really a agreed upon established framework dictating what these meaning layers actually are. So recently, a survey paper by Pondiani et al. Came out that takes a look at the existing vision work that we have in the field. And from all of this, they constructed a computation-centric taxonomy based on the existing benchmarks that we have. They established three main layers of semantics based on all of the vision papers that they surveyed. The lowest layer is raw features like edges, color, and textures, the sort of thing that you'd expect like the early layers in a convolutional neural network to extract. And then this middle layer, you have objects and regions, which makes up the majority of existing computer vision work as of 2023. And then they establish high-level concepts, which they define as stuff like events, emotions, aesthetics, symbolism, things like that. And so humans can pretty easily synthesize the low and mid-level features to derive high-level concepts from visual content. And so ideally, we'd want computers to be able to do the same thing. Pondiani et al. Define this as comprehensive visual understanding. However, vision research, as I alluded to, has historically focused very heavily on this middle layer here. So what work is actually being done on bridging this gap and moving into the high-level semantic understanding? Pondiani et al. Argue that the lowest level of these high-level concepts can generally be described through event semantics. This is stuff like activities, object purposes, object relationships, actions, interactions. In the paper, they define this category as common sense semantics because compared to the other abstract concepts that they define, these event semantics are fairly objective and can be described using logical frameworks. And so I'll be referring to the task of understanding this suite of event-centric information as visual event semantics. At a high level, the overarching goal of visual event semantics is to answer the question, what's going on in this image or video, in a sort of logical and organized manner. So especially as stuff like vision transformers continue to improve, there's starting to be a set of incipient work on visual event semantics being tackled. However, the methods that exist tend to focus on pretty simple events, like similar to the stuff we've been seeing in action recognition tasks for the last 10 years or so. And so given the power of existing vision language models, the question is sort of how can we use what we have to sort of push things forward, to start extracting more complex events from visual content like we see in event extraction in text documents. So the problem I want to consider in this talk is how can we model and understand complex event semantics for multimodal data? I'm going to give an overview of three projects that all sort of explore this problem from different but related perspectives and give background context on some relevant literature where appropriate. I'll start by giving an overview of the existing work in visual event semantics for images, and then discuss a study that explores the limitations of the task framing of this general body of work. And then we can take a look at how the ideas explored in image event semantics can be adapted to the video domain. And I'll give an overview of the data set that we have constructed for exploring this. And then finally, I'll give a brief preview of some in-progress work exploring how complex content can be modeled and reasoned over in the multimodal domain. So most of the work on visual event semantics takes place in the image domain. So let's go and start there. Naturally, an initial framing of this problem has been the task of just classification, event recognition. So given an image of something happening, a model should be able to classify it into one of n event types. And so, okay, cool. On limited domains, this can work well with existing image classification models. However, with this framing, as the domain gets more diverse and the complexity of the events increases a little bit, you can start to run into problems with this setup. So in a lot of cases, 1 or 2 word descriptions of events isn't necessarily sufficient for comprehensive classification of event semantics in various images. For instance, consider the event of like catching something. Given only a short like classification task-oriented event description, both of these events are basically treated as the same thing. And evidence suggests that humans just don't categorize events this way. For some quantitative data, as supporting evidence, I'm stealing an example from a talk given by Mark Yatskar. So both of these people are pouring beer, and in the event classification framework would be considered the same event. However, when 100 AMT annotators were asked, is the same thing happening in these images, the majority indicated that it wasn't necessarily the case, indicating that the answer to the great event semantics, what's happening here question is different for these 2 images for a lot of people. And so motivated by this idea, some computer vision researchers turned to frame semantics, or the idea that events can be described by a semantic frame or template of information pertaining to that event. Gupta et al. Reframe event understanding as a template filling problem as opposed to a standard classification problem. So given an image, a model must classify the action, the agent, and the instrument where applicable. This solves the problem that we saw earlier with the 2 catching images. And so then Yatskar et al. Built on this work, replacing the 3 entity templates with event templates provided by the FrameNet database, which is a large collection of these event templates that describe various verbs in the English language. And so they renamed this task situation recognition, and it's become more or less the standard task for event understanding for images. The general approach that's developed for it is to first identify the verb taking place in the image and then go and fill out the rest of the template's roles, which tends to work pretty well for simple events involving a verb and a couple of related entities. Maybe these events, they're like a bit more complex than an atomic action that you'd see in an action recognition data set. But what about longer, more complex events, like a wedding or going to get a COVID vaccine? So how well can the images depict these events, and how can this framework represent these events from just images? Is there enough context that the images provide? So I'm going to be going over a project in which we explore these ideas and basically find out that single images for these larger, more complex events can be quite ambiguous and subjective, and this framework sort of falls apart. So let's take this image right here. What's happening in this picture? Maybe he's eating, maybe he's just standing or panting or something. We don't have enough contextual information to establish a meaningful distribution of the things that could be happening here. But this picture is actually a screenshot from a video. So let's go and pull another frame from here. Okay, so another dog is definitely eating and with a blindfold on its head. We're able to start hypothesizing, constructing hypotheses about what's going on here, but there isn't necessarily enough data to be certain about it. You pull a third image from the video, and now we have enough context finally. And so all of these images depict a birthday party for someone's dogs, but with significantly varying levels of ambiguity. So we asked Amazon Mechanical Turk annotators how likely it was that each image depicted a birthday party. And we got these average scores. I honestly think that 6% is a little high, but the psychology of human certainty judgment solicitation is another topic. At least it's low. Looking at images like this, it raises the question, how common is it for images to be ambiguous with respect to the content that they're depicting like this? And so obviously it depends on the distribution that you're pulling from. If we only pulled images from like the headline page of the New York Times, we'd probably get pretty clear images most of the time. But do we really want our vision models to only be able to reason over New York Times headline images? At the very least, we want these models to be calibrated so when they are given something ambiguous, they can output a reasonable response, akin to how humans here were able to provide human judgment scores for how likely it was that these images fell into different events. So to collect a set of images that better align with these real-world distributions, we sampled 12,000 images from YouTube videos of specific events, and then took a subset of these and asked annotators to rate the likelihood that the images depicted the events shown in the video they were taken from. We got this distribution of scores across the board, and so while a lot of the images are clearly pretty clear, there's a pretty substantial portion of the images sampled at random that just aren't. And so based on this, we had a couple of questions. So firstly, how do these situation recognition models actually perform on this ambiguous data? 2, can training on these ambiguous images improve performance of these models? And then 3, can the human annotations we collected actually be used to assess model calibration approaches? For question 1, we found that the answer was not great. We assessed the event type classifier alone without any role labeling and found that anything that humans scored below 80% confidence ended up getting about a 20% accuracy from the situation recognition models. Interestingly, though, we found that if we took the top 10 accuracy of these models, there was a very clear alignment between the model accuracies and the human certainty judgments, indicating that there is information about these events that the models can extract from these ambiguous images. It just isn't enough for the models to be certain, similar to humans. So this sort of motivates, maybe we can produce calibrated models on this sort of content. We found that training on this ambiguous data did improve model performance on other noisy data, which motivates more of a focus on using ambiguous data in training sets. And then we found that using uncertainty quantification techniques like label smoothing and focal loss, relaxed softmax, actually causes the model's output logics to align better with the human judgments, indicating that the human judgments may be a good method for assessing the calibration quality of models. So finally, we took all of the ambiguous images produced from this project and the annotation certainty scores that we solicited and put them all into a data set called Squidy. And in the paper, we delve into some other ideas like annotator disagreement. So when 2 annotators give very different certainty judgments for an image, when and why does that actually occur? So based on this information, it isn't necessarily clear that images are the best way to model complex visual events, given that the ambiguity that humans rate when looking at many of them. So we ran a quick AMT study to see if there's a significant difference between images and video footage. We grabbed a couple hundred of the images from the Squidy dataset, and remember that all of these images were pulled from videos originally. And so we grabbed the 2.5 seconds before the screenshot was taken up to the 2.5 seconds after the screenshot was taken and presented Mechanical Turk annotators with these 5-second clips and basically asked them the same question. So at 0 seconds, what is your certainty that this event depicts XYZ? At 2.5 seconds, what's your certainty that this video depicts XYZ? And then after 5 seconds, what's your certainty? And so most of the videos are well over a minute long, but even after just 5 seconds of context, 50% more annotators reported high confidence about the content of the video after watching the 5 seconds of content. So video clearly provides helpful semantic context that was missing from the images. It's not super surprising. We saw that the more frames you pulled, the more certain you became about the content. And so it's not a huge leap to assume that video content might be a better domain for visual event understanding at a high level. There's a little bit of work that's been done on video event semantics. A lot of it is just like a direct copy of the work that was done on the original images in the situation recognition work. So keeping it to pretty simple atomic events that aren't a whole lot more complex than action recognition we've been seeing in the past 10 years. And so it's sort of an open question for how complex event semantics can be studied in the video domain, if we want to consider things that are more complicated than simple atomic actions. So what kind of visual events would we want to consider for studying complex event semantics? And can we leverage any existing data sets for this study? To answer these questions, we established a set of 5 main criteria for a video data set to study complex events. The first is complex event depiction, obviously. We are interested in the relationship between complex hierarchically defined events and natural language representation, specifically events that need more than just a simple sentence to describe what's happening in them. And so we require that a data set actually contain this sort of information. We also would like diverse events and formats. We don't want to produce a model that just really understands exactly how weddings work and nothing else. For format, same sort of idea. Different information is depicted in different ways depending on the type of video that you're looking at. Say, for example, like a professionally developed news broadcast versus like raw footage that someone uploaded from their iPhone. And so we want to explore the difference in how these events are depicted from different content. We'd also like multiple videos per event for the same reason. The more videos you have for a single complex event, the more context you have, the better comprehensive understanding you can produce. And then we also would like this data to be reflective of the real world. A lot of TV and movie data, it tends to intentionally be developed so that humans can easily understand it. It's very nicely curated. So it's sort of similar to the New York Times image example that I was giving earlier, where, yeah, it's easier to extract information in these domains, but it doesn't produce particularly robust models. And then finally, we'd like these videos to also be able to be paired to text documents. So you can actually sort of have a ground truth of what event is taking place without a substantial amount of format specific like representation of these events. And so given the criteria, we took a look at the existing event-centric video datasets out there. We found a bit over 70 of them, but found that none of them actually satisfied the criteria that we came up with. The closest thing that we could find were TV shows and movie datasets, but again, that's nicely curated information that isn't necessarily reflective of noisy real-world information. For other data sets like action recognition, video captioning, and QA data sets, they typically either suffer from event simplicity or limited event type diversity. Or for the ones that actually follow into both criteria, there isn't an easy way to develop text documents that could be paired to them. And so we developed a new data set called Multivent, which stands for multilingual videos of events with aligned natural text. It is about 55 hours of video, which is on par with existing data sets like MSR-VTT and LSMDC. It contains about 200 or well over 2,000 videos and paired text documents, and it covers 260 events in over 40 countries, each with paired long-form text documents. We collect data in 5 target languages: Arabic, Chinese, English, Korean, and Russian. A big problem with a lot of multilingual video data sets that exist is the content tends to be collected only in English and then translated into other languages. And so you end up with a lot of biases like translationese and just artifacts that aren't particularly representative of like a global population. And so we specifically pull a video and text content that was directly produced for speakers of our target languages to eliminate that factor. To get a better idea of what the data set actually looks like, here's an example of a data point. Each data point consists of a video sort of anchoring the other content. The video depicts some current event from our set of 260. It was produced for speakers of one of our 5 target languages, and it's paired with a text description that's in that same language. And then for each of the events, we also include a set of 1 or 2 long-form text documents, which usually are Wikipedia documents. We have 1 in English, and then if the target language is not English, we include a second text document that's in that target language as well. So the data collection process is fairly straightforward. We broke down typical news coverage topics into 4 main categories: disasters, political coverage, social events, and business and technology news. We then identified our 5 target languages that we wanted to cover: Arabic, Chinese, English, Korean, and Russian. And then we find the list of the top 5 countries with the highest percentage of speakers of each language, and then go onto Google Trends and search each of these countries for the past 10 years of top Google search material, basically. We collected the visually representable events that also contained a significant amount of news coverage. And then we scraped social media for 10 videos for each of these events. We tried to, in this scraping, collect from multiple social media sites. It ended up primarily being YouTube and Twitter. This was back when you could scrape Twitter. And we also attempted to get a variety of video formats. So we got some professionally developed news broadcasts. We also got vlog type edited footage, and then just raw footage from people's phones. And we ended up with a nice distribution of locations, over 40 countries, a nice distribution of years, past 10, definitely focused on the more recent, like 2019, 2020, and video formats. So with all of this data, we decided to see how it did as video data for information retrieval, specifically video retrieval. We used the text descriptions as queries and then tried out some existing video understanding models. They did pretty well on text data, on English data, about as well as you would expect them to do on a general data set, maybe a little lower. But then when you had them try to do retrieval on non-English data, their performance plummeted, which isn't super surprising. So what we did was we developed a model, multi-clip, which is very similar to the clip video understanding model. We replaced, though, the vision transformer with a transformer trained on the multilingual Lion 5 billion dataset, and replaced the text encoder with an XLM Roberta model. And then we went and did a pooling mechanism for all of the frames in the video. We sampled like 12, I believe, and then pooled them all together for a final output. And so this new model performs comparably to the other 2 video understanding models. We ran it on some more models, but these are the 2 most representative ones. And then for non-English data, as you would expect, the performance drastically improved, sort of motivating actually training your models on multilingual data for multilingual understanding. We've been annotating the semantic content of this data set for quite a while now. Essentially, what we're trying to do is identify all of the visual entities in the videos that help to explain the current event that is being depicted in the video. And so as a small study, we took about a 200 video subset of the annotated footage and ran an analysis on the differences in how the event information is produced for the different formats. And we had 3 main formats that we divided the data set into. We had professional news coverage, which made up about 53% of the data set. We had edited unprofessional footage like vlogs, and then we had unedited raw footage like iPhone videos. And so it isn't super surprising, but it is striking the difference between the amount of content that is shown in professional footage versus like raw footage. The professional footage had about 9 times more on-screen text content like OCR than raw footage, and 3 times as much than edited footage. And then the difference in visual content, it's less extreme, but still fairly drastic. The professional footage tended to have about twice as much relevant event-centric visual content than the raw footage did. And so aside from raw event extraction and information retrieval, there's a lot of interesting uses for the data set aside from the multilingual video retrieval, which was our initial focus. Other uses for the data set include video summarization, report generation, variety of question answering tasks. And I bring this up because the data set and its applications are going to be forming the basis of the 2024 Scale Summer Workshop, which I'm helping to organize. I focused more on the vision-centric side of things for the data set, but it provides a lot of opportunity for language work, speech work, multilingual and multimodal work. So if any of that content that I've been talking about seems interesting to you, consider looking into Scale for this summer. I think some information will be coming out pretty soon. And so to finish off, I'd like to give a preview of some in-progress work on complex visual event understanding. We've been talking about the issues with exploring and studying visual events with images and how we can potentially do a better job by using video, understand more comprehensively. But I haven't really talked about how you could actually approach the problem and try to reason over this content. So, as I've alluded to, there's powerful joint modality transformer models that encode vision and text data together, and they perform pretty well on a lot of benchmarks. Here's an example of an actual architecture. It's not more complicated than this one here. It's just a combination of vision and text encodings and a multimodal transformer with some frozen layers. But if you actually try using models like this for downstream applications, particularly for vision-heavy work, it becomes pretty clear that the models heavily rely on text content and biases from pre-training when generating outputs. And it's not super clear whether or not they're performing any multimodal reasoning at all. So for example, here's some frames of Joey throwing a ball. But if you ask the frozen BiLM model that I showed back here, which is state of the art on this data set, if you ask it what he's throwing, the outputs are mostly nonsense. And you could argue, okay, the ball's kind of small, but you see this pretty consistently on visual data that you ask these models about. I've tried like other pairs of image text content where it'll say there's a tree in the middle of the ocean or things like that if I don't provide any text data. And so the lack of visual understanding is a pattern that's beginning to be documented. Papers have been coming out that use probing techniques to assess the visual reasoning ability of these models. And they find that the models typically don't leverage much joint modality understanding at all when they reason over multimodal content. Another problem with these models is the fact that they're giant black box transformer models, and so they can't scale up to longer videos super easily. So for example, on the TVQA data set, which these frames are from, where models are asked to take in a minute of video footage and answer questions about it, I think only one of the approaches listed here actually takes in the full minute of content. The rest only take like a ground truth of like 6 seconds, like a 6-second window that is annotated as describing the answer to the question, and they operate over that input only. So for multimodal reasoning, it'd be nice to have a system that's both scalable to work with longer footage and also interpretable, so we can see exactly how it's reasoning over the multimodal data and what evidence from it that it's actually using to answer questions. So we draw from work in neurosymbolic entailment tree generation, specifically drawing a lot of influence from Nathaniel's very cool work on the topic in the text domain, and to put together an entailment tree generator for multimodal content. We focus on generating a system that can work with the TVQA dataset just as a baseline application, and want to construct a system that can take in this TV show clip and subtitles and then construct proof trees to answer multiple choice questions about the TV show content. We're currently, we're working with the TVQA dataset, and here's an example data point from it. They provide minute of video frames sampled at 3 FPS and a transcript of like 20 to 30 lines of dialogue. And they ask a multiple choice question that typically requires reasoning over both the vision and text content. And so before going over the architecture of our proposed system that we're working on, let me give an example to illustrate what this proof system would actually do, or what it's actually doing. So here's a simple output for an easy question to give you an idea. This is an example of a data point in the TVQA dataset. You have your video content, you have transcript. I pulled out a frame and a single subset of the transcript here. And they ask a question like, what drink bottles at the table when these characters are talking to each other? And so we're currently in the middle of running experiments for this data, or for this data set with our system, but here's one of the outputs that we're currently getting with it. When you pass this question into the system, it first converts the question answer pair that you pass in into a hypothesis. So the drink bottle is beer. Given the amount of complexity in this sentence, it's unable to prove it at the current level with the information it has from the vision and text data. So what the system does is it decomposes this hypothesis into two parts. The drink bottle is at the table and the characters are talking to each other and the bottle is beer. At this point, the left node is now simple enough to prove given the visual data that we have. And so there it is, there's the visual evidence. And then it decomposes the right node one more time to make it a little simpler for proving it. So the second node here is the characters are talking to each other. It can directly prove that from the dialogue. And then the drink bottle is beer can prove that with the visual content. So how do we get a model to actually output things like that? The proof generator, it works based on three main modules. The first is retrieving facts about the text and video content. So these things here. Then two, filtering these facts given a hypothesis to see if any of the facts actually entail that hypothesis. And then three, if none of those facts entail the hypothesis sufficiently, then it decomposes the current hypothesis into two sub-hypotheses that it then recursively tries to prove. And so here's the general system. You can see the dotted circles around some portions. These are the three main modules that I was discussing here. The dark blue right there, that's all of the fact generation for the text and vision modalities. The light blue is the filtering of those facts, and then the yellow is the decomposition. So before we get into the main system with the three modules, what the system first does is it turns the question answer pair that it's given into a declarative statement. The proof system, it works over hypotheses, both for generating facts, filtering them, and then decomposing them, similar to Nathaniel's Nelly proof generation system. Once the question answer pair is declarativized, then we can move into fact generation based on the data. Specifically, the transcript, we first sample text with a cross-encoder trained on MS Marco. And for the video clip, we extract the frames that align with this extracted text information. And then for the text content, we generate a set of inferences with GPT. Unfortunately, the text models that exist aren't particularly good at doing entailment for hypotheses over like TV show transcript type data. And so we need to use this step of generating inferences with GPT in order to extract information that is operatable with existing models. So once we've generated these inferences, then we go and pass the hypothesis and the inferences from the transcript into a cross-encoder trained on SNLI and multi-NLI to see if there are any facts that entail the hypothesis. Then we go, and if there is a fact that entails the hypothesis, great, we're done. Otherwise, we go and pass the hypothesis into GPT and have it decompose it into two sub-hypotheses that we then recurse over. If we reach a maximum depth of the proof tree that you set beforehand, then you go and query a vision model on the frames that you have at the most granular incomplete sub-hypothesis nodes that you have. And if the model is able to find a frame that entails the hypothesis, then great, then you're done. Otherwise, the proof can't be completed. For the vision model, we use a lava model that basically acts as a visual question answering system. You go and actually what we do is we take the hypothesis or the sub-hypothesis, convert it back into a yes/no question, and then pass that in alongside the frames. And it'll output yes or no for whether or not the frame entails that information. And so that's the general system. To summarize what I've talked about, the big question I've been focusing on is how can and should we study decompositional event semantics for visual content? We started off with an overview of frameworks through which visual event semantics have been approached for image content and explored how using templates to represent events can result in more nuanced and human-like classifications. Then we explored how image-based event semantics approaches can fail for complex events where individual images may not provide enough context for event identification and understanding, resulting in ambiguity and general subjectivity. And so then we look into adapting these ideas proposed in image semantics works to video domain and explored what a data set that could facilitate this sort of study would actually look like. To this end, we introduced multivent, which basically is our proposal for a model that, or for a data set that can be used to study this sort of information. And through it, we assessed differences in event depiction among different formats and took a look at multilingual video information retrieval. Finally, we discussed in-progress work on end-to-end multimodal reasoning systems, specifically a scalable and interpretable model that makes use of work in neurosymbolic entailment tree generation for text, and showed that it can generate proofs that show exactly what information it's operating over and how it is synthesizing that information to produce outputs. And that paper should be coming out soon, depending on how much longer experiments take. And so here are just a few of the excellent people that I get to collaborate with on these sorts of projects. So big thanks to all of them. And I hope that this talk helped to highlight a bit of the fun research problems that exist in multimodal understanding. So thank you. And I'd be happy to take any questions. It looks like we have a bit of time. Yes.
I'm wondering if you can go back to the, I'm not sure if you're ready to specific slides, but I'm wondering if you can elaborate on how you manage to separate ambiguity of your annotations in this first part of your talk from just being slow, like annotators are much inaccurate. And then oftentimes people use to annotate your agreements to get rid of the noise, but then you cannot really make that kind of proxies to distinguish what is noise versus what is a genuine ambiguity.
Yeah, that's a really good question. In terms of just annotator quality, we did a pretty thorough vetting of the mechanical Turk annotators before we gave them access to the full task. We ran a series of pilots in which we gave a set of specifically curated images, and then that there shouldn't have been ambiguity on, or there are like specific pitfalls that clumsy annotators would fall into. And we went and filtered out annotators based on that by then applying a couple of heuristics. So generally, I feel like the quality of our annotators wasn't bad, but in terms of the difference between like epistemic and aleatoric uncertainty, that's very much a existing like issue. And so, yeah, when you take the median certainty scores provided by these annotators, you're removing that information. We explore when and where annotators do diverge in terms of certainty judgments in the paper. We find a couple of specific types of disagreement that tend to arise. But in general, we do sort of omit that aspect of the ambiguity when we are running those experiments on the situation recognition models and the model calibration technique. So you're right, that is a bit of information that we don't consider for a lot of the experiments. Yes.
That was a very interesting talk. So building on the ambiguity part, when you include a 2.5 or 5 second video, are humans less? Is it just that they now have more? Like there's a few informative frames, and now you just hit those in your 5-second clip, or do you think it's something specific about the video itself?
That's a really good question, because yeah, this study that we included, let me go back to it. If I can find it. There we go. This isn't included in a paper. This was a post-paper analysis that we did, sort of exploring it. And we found that the psychology of annotating certainty for videos is different than annotating certainty for images. We found, you can see here, there's that little spike there at certainty score of T0. We found that annotators were a lot more likely to sort of like stick to like 50% at the start of a video because they knew that they had time to make their decision overall. Whereas for images, it's just like a one and done. You either have low certainty or high certainty. So to an extent, these annotations are almost certainly affected by the modality shift to video. And so it's not entirely clear how much that is the case. We're more going off of, this is a motivational example just because of the end result in terms of how certain people tend to be. But yeah, there is definitely a domain shift that isn't necessarily fully explored here. Yeah.
Did you test it on the time or like video isolated with this different gear?
No, we have not, but we want to run a study on that because I think that would be really interesting. We just stuck with 5 seconds, but what would be really cool is to sort of run a whole lot of studies along this line, sort of seeing exactly how human certainty scores change across a video, and then you could develop sort of like a Bayesian-like model for human understanding on video content. Yeah.
Also, please address the elephant in the room, GPT-4 with vision models. How do you put these efforts in that perspective? Like clearly there is a lot of, there's like the whole side of the community that they're going through. They're trying to solve the same set of problems, similar set of problems, but from like very different approaches. Do you feel that these are competing approaches, or these are maybe complementary? How do you see it?
I definitely say complementary. Like the neurosymbolic proof generator that we use, this is built on large language models. We're using GPT 3.5 and Lava to produce these proof trees. I think that this sort of work of sort of interpretable image and video understanding from a human perspective is tackling a sort of different problem in that we aren't necessarily concerned quite as much with just the final output as we are with understanding how it's actually able to put all of the pieces together and synthesize the information. And so I definitely think that they're complementary as opposed to competing. Thank you.